Hello, my name is Elide Herrera Valdez, and I'm excited to talk to you about evaporation-driven capillary flow in paper-based microfluidic devices, as we believe that they may be the key to solving a severe global problem. People in the least developed countries have a life expectancy that is about 25 years lower than people in the most developed countries. And although there are many factors that contribute to this, one of the main reasons is the access to healthcare. And because this is a major issue, the World Health Organization made an urgent call for the development of diagnostic devices that can work under resource-limited settings, which are places that might not have access to clean water, electricity, or trained technicians. Fortunately, one of the platforms that has emerged that fulfills the necessary criteria are the paper-based microfluidic devices, also known as MicroPADS. And MicroPADS are essentially a piece of paper that has been patterned with wax. And when you add a solution to it, the solution will move across the channels via capillary flow and will later produce a signal that can serve as a way to diagnose diseases. And because MicroPADS rely extensively on capillary flow, it is crucial that we have a complete understanding of this in order to unlock the full potential on this type of devices. Here is where our investigation comes in. There are two modes of capillary flow that can occur in MicroPADS. On the left side, you can see the traditional capillary flow, which is the most common, and you have probably seen this whenever you clean up a water spill with a paper towel, as this is the movement of a solution across a dry paper, or in this case, a dry channel. We have the Lucas-Washburn model that helps us describe the rate of the capillary flow in paper. And this model is specific to the paper and solution that we used. This model also tells us that the rate of the capillary flow is inversely proportional to the square root of time, which means that the solution will get slower and slower over time until it stops. On the other side, we have evaporation-driven capillary flow, or EDCF for short. And this is the movement of a solution across a pre-wet channel. This is driven by evaporation taking place at the end of the channel, which we call an evaporation zone. This type of capillary flow has not been studied on paper before and is the focus of our investigation as we seek to develop a mathematical model that will describe the rate of EDCF in MicroPADS. And in order to do that, we can only assume at this point that the rate of EDCF is proportional to the evaporation rate, and we assume that they are constant, and I will prove that to you in a little bit. We are also using the Pignett-Vexen's evaporation model that describes the rate of evaporation of a droplet of water. And this model has 4 different factors, which are the physical properties of the solution, the size of the droplet, a function of temperature described by the equation below, and also 1 minus the relative humidity. Now, if we assume that our evaporation zone behaves like a droplet of water, we also predict that the EDCF rate will be proportional to the radius of the evaporation zone, to the function of temperature, to 1 minus the relative humidity, and also to the design of the device itself. And here is how we tested them all. We first fabricated our devices by printing our wax pattern into a piece of chromatography paper. We sandwiched it between 2 pieces of laminating sheets in which one of the sides had a hole that served as the evaporation zone. We took our device inside the environmental chamber where we could control the temperature and humidity of the environment, and we submerged the bottom of the device into a bath of nanopure water for 1 hour. We then switched our device into a new bath of red dye solution, and we tracked the movement of the red dye solution moving across the channels. Once we gathered our data, we were able to do a variety of plots that I'm about to show you. And here is the first one. Here you can see a comparison between the traditional and the evaporation-driven flows. You can see in this distance versus time plot that we have two sets of data. The red data represents the traditional capillary flow, and the blue data represents the evaporation-driven flow. As you can see, the traditional capillary flow is being compared to the Washburn model, and we can see that they match. We can also see that the evaporation-driven flow is being compared to the EDCF model that we had predicted, and we can also see that they match. So because of this, we can confirm that the rate of EDCF is proportional to the evaporation rate. And because the slope of the line is constant, we can also confirm that the rate of EDCF is also constant. Now that we have confirmed this, we can move on to test the different parameters of the model in our devices. And we started by testing the evaporation zone radius. And here you can see that as we increase the size of the evaporation zone, you also increase the rate of EDCF. We have to point out that there is a limit to how big the evaporation zone can be in order to work this way. Because when we take a look at the plot, we can see a rate versus the evaporation zone radius plot, and where we can see that EDCF data being compared to our predicted model, and we can see that between 0 to 4.5 millimeters, the EDCF rate is proportional to the evaporation zone radius. Then we moved on to test the parameters of the channel. And here you can see the length and the width. If you take a look at the top picture, we tested 3 different lengths of channels in our devices. And regardless of the length, as you can see, the EDCF rate remains constant. But when you take a look at different widths of the channels, you can see that as you increase the size of the width, you actually decrease the rate of EDCF. And here are my plots. On the left side, you can see the rate versus the channel length, and where we can confirm that the EDCF rate remains constant. And when you take a look at the rate versus the channel width, we see that the rate is actually inversely proportional to the width of the channel. And we also infer that this happens to the thickness of the channel, as they are very similar type of terms. Then we moved on to test the environmental conditions in our devices, and we started by testing the temperature. Here you can see 2 different sets of data being compared to our EDCF models in this rate versus temperature plot. And as you can see, our data matches our predicted models, so we can confirm that the EDCF rate is proportional to the function of temperature, which is described by the equation below. And when we take a look at the relative humidity, and again, compare 2 different sets of data and compare them to our EDCF model, we can see that the rate of EDCF is proportional to 1 minus the relative humidity. Now that we gather all our data and we were able to go back to the PMV evaporation model, we finally developed our new EDCF model to describe the rate of capillary flow in paper, which has now 5 different parameters. 3 of them remain the same, which are the physical properties of the solution, the function of temperature, and 1 minus the relative humidity. And the other 2 terms have to do with the design of the device, which are the radius of the evaporation zone, and also the functions of the width and thickness of the channel. In conclusion, we developed a mathematical model to describe the rate of EDCF in MicroPADS. We found out that the rate is affected by the design of the device and also by environmental conditions. And lastly, this model can now be used in the designing of improved diagnostic devices to help increase the life expectancy in the least developed countries. Now I want to take the time to acknowledge the National Science Foundation and William and Linda Frost Fund for funding this project, also to my advisor, Dr. Andres Martinez, and to all the members that helped throughout the project. Thank you very much for your time, and I look forward to answering your questions.